So let us discuss the solutions to assignment 5. We are given that the input transitions from VDD down to 0, which means that the PMOS turns on and charges up the capacitor to VDD, because we've assumed that the capacitor starts at 0 volt. Now we are asked to find which of the following statements are true, right? The answers are of course B and D, but let us see why A and C are not true. For one thing, we know that the energy supplied by VDD tends to, because this capacitor now charges up to VDD, the energy involved will be greater than or equal to half CL VDD square, right? But of course, if you work out the math, you can work out the math as follows. So the current in the capacitor will be the current through the PMOS, and of course also the current outside coming out of the source VDD. The current, let's say that's I, is equal to and let's call this as V, right? Let's call that V. The current is equal to CL dV by dt, which means the energy supplied by the supply is equal to the integral of the power dt. The power is the voltage at this node, which is VDD, into the current coming, right? This is of course equal to the same as the current going through the supply, the current going to charge the capacitor, which is CL dV by dt, right? You can of course take VDD into CL outside, and this goes from 0 to infinity. So the idea is that the energy at time t is equal to go from 0 to t, this plus the energy at 0, right? So the energy at 0 plus the extra energy. Now what is E of 0 going to be, right? So if you look at less than 0, so E of 0 is the energy spent by the supply as at the 0 instant. That is the total energy spent by the supply as of t equal to 0, right? So less than 0, you can see that there's no current since Vn is equal to VDD for t less than 0. There's not this PMOS is going to be off, so it's just an open circuit. I mean, since we are assuming the transistor is ideal, and which means of course that the for less than VTH, for VGS less than VTH, it's going to be off. That is the definition of the ideal transistor. So you're not going to, so this is just going to be an open circuit, and which means the current will have to be 0 necessarily. That means that the power is 0, which means the energy is 0. So for less than 0, the total energy, which will be the integral of the power, will be 0, from minus infinity to 0, right? So E of 0 is equal to 0. So we will just ignore that. Now let's actually perform this integral. You can bring the constant terms VDD and CL outside. This is 0 to t dV by dt into the integral with respect to t dt, right? So now of course we know by the fundamental theorem of integration that this is VDD into CL times V of t minus V of 0, and question itself says that this is 0, right? Question says that the capacitor voltage is 0 at t equal to 0. So that goes away, and what you're left with is VDD CL V of t, right? And you can see that in the limit, right, since we are saying that the capacitor is charging up, in the limit this will become VDD square CL. This is as t tends to infinity. So there's no dependence on the t parameter here. So therefore this is wrong. And as we've just noted, right, VDD of t, energy of VDD just goes to CL VDD square, right? And so this is correct. And since B is correct, uh, and the capacitor, the VDD is not equal to 0, right? Because clearly I've demonstrated that VDD is not equal to 0. That means that CL VDD square is not equal to half CL VDD square, right? So therefore the third option is wrong. Of course, I'm also assuming here that CL is not equal to 0, which means the product of those two is not equal to 0. Now for option 4, let us actually derive the energy of the capacitor and the energy of VDD given time. Now for ECL of t, one has the capacitor, and this is the node voltage V. This is the current into the node. So for ECL, the energy stored in the capacitor or the energy dissipated in the capacitor. So this is passive convention, right? For energy stored, it would be the passive convention. For energy supplied, it is the active convention where you have VDD and then you have current coming out of it, right? So that is active convention, this is passive convention. So yeah, positive direction of current is into the voltage source here. So we now have VI dt integral 0 to t plus E naught. E naught, as we have already discussed, is 0 because the capacitor will be floating. Will be charged to 0 initially, and there's no current through. And then, so this is integral 0 to t V into CL dV by dt, which we can just do as integral 0 to t V dV by dt. Now V dV by dt is equal to d by dt of V square by 2. So this is equal to CL integral 0 to t d by dt of V square by 2 dt. And this is equal to, of course, CL V of t the whole square by 2 minus V of 0 the whole square by 2. And as we know, V of 0 is 0, so that goes away. So this is ECL of t greater than 0, right? And yeah, this is also, of course, this expression is also, of course, t greater than 0, and all the other expressions that follow as well. So this is CL of t. And yeah, so similarly here, t greater than 0. Sorry, that would be VDD of t. This is EVDD of t. And similarly, if you do the derivation for EVDD of t, which is just going to be equal to integral 0 to t Now instead of V, it will be VDD into C dV by dt dt. This is the voltage, this is the current coming out of the voltage. Yeah. And then this is equal to integral 0 to t, VDD comes out, CL comes out, dV by dt dt, which is simply VDD CL V of t minus V of 0, and this we know is 0 because this is the capacitor voltage, right? Capacitor voltage is initially starting at 0 to V of t. So this is EVDD of t for t greater than 0. Similarly here also t greater than 0. So now that we have both expressions, so thus we get that V of t is EVDD of t by VDD CL, right? And substituting this now for V of t in this expression, we get VCL of t is equal to CL into VVDD of t by VDD CL square and these terms into 2. So therefore CL and CL, the square term gets cancelled here. So EVDD of t is equal to VD square is equal to VDD square into CL ECL, right, divided by 2CL ECL. And that therefore EVDD of t, because now we can take the positive square root on both sides because we know that all the quantities in here are positive. In fact, EVDD will also be positive because we have given it as the energy spent by the supply, the energy supplied by the supply, right? Not the energy dissipated by the supply. So this will be VDD into 2CL ECL the whole root, right? So since the CL is missing here, it's just saying 2 into ECL. Option D is wrong. Question number 2. Circuit is running at a frequency F with supply voltage VDD. The frequency is increased to 16F, right? So P dyne is equal to C VDD square F. Now the new power is equal to C times VDD1 square 16F. We want to know what is VDD1 such that P equal to P dyne, right? So therefore we just substitute VDD1 square 16F is equal to C VDD square F, right? That goes away, and of course these two also cancel. So that means if you take positive square roots on both sides, this will become by 4, which means it's a which is equal to 0.25 VDD or 25% of VDD. So the answer here is 25. In question 3, if a minimum length and minimum width transistor sees local VT variation of 27 millivolt, then what about one which has 9 times the width and the same length? The idea is that delta VT is going to be inversely proportional, local variation, that is delta VT, is going to be inversely proportional to the square root of WL. So what we are saying is delta VT1 is equal to 27 millivolt is equal to some constant of proportionality times WL. Now what is going to be delta VT2 for 9 times the width, 9W times L? This is now going to be K times 3 WL, which is, now since this is delta VT1 by 3, right, which is 27 milli by 3, which is 9 millivolt. And since we've been asked the answer in millivolt, the answer is 9. Which of the following statements about a static CMOS inverter are false? The answer is A and C. So let's look at the false options first, right? Static current from VDD to ground is 0 if PMOS and NMOS are ideal. So this option is true, right? That's because at least one of the transistors, the input voltage is always some CMOS level voltage, which is like V0 or VDD, which means either the NMOS will be off if it's 0 and the PMOS will be off if it's VDD, and therefore at least one of the transistors is cut off, which means the current is 0, right? So the static current has to pass through both transistors, and if one of them is cut off, then that current will have to be 0. The current to ground has to be 0. Now if the NMOS transistor has leakage and the PMOS transistor doesn't have leakage, the output voltage will not swing all the way to VDD but will swing all the way to ground. The idea is that now the NMOS transistor is leaky. That is, now let's say that the input is at VDD. Let's say that the input is at 0 volt, right? And the PMOS is alright, but the NMOS is leaky. So what will happen when the input swings from 0 to VDD? So when the input is 0, the PMOS is on strongly, but the NMOS is off in subthreshold region. So both of them will, so both the NMOS and PMOS will fight, right? And if this is VDD, then since both of them are fighting, the output voltage will never actually fully reach VDD. So you'll have to take that as not being reaching fully VDD. But then when the input is VDD, the NMOS is fully turned on and the PMOS is fully turned off, because the PMOS doesn't have leakage. It's an ideal PMOS, and so therefore it's essentially an off switch, and all the output voltage is determined by the NMOS. So that's fully to ground, but not fully to VDD. So this option is also true, right? But of course now since if you notice, the first option is just the converse statement, and so therefore the first option is false, right? It's not the converse statement, but it's a statement with the conclusion with the conclusion that is like the exact opposite as it's the same premise. If the NMOS has leakage and the PMOS doesn't have leakage, so it's the same premise, but the conclusion is the exact opposite, right? So therefore the first option is false, and we've been asked in this question which are the false statements. So the first option is one of the false statements. The functionality will never depend on the relative sizes of NMOS and PMOS transistors. Now this is not true, because if one transistor has leakage, let's say for example that the PMOS has leakage and the NMOS is okay, it doesn't have leakage, but the PMOS is very large and the NMOS is very small, right? So even if the input voltage is VDD, the PMOS will turn on. It won't be on, but it will be conducting in subthreshold. So both these guys will fight, and the voltage that they'll resolve to will depend on the strengths of the two transistors. So WP is very large and WN is very small, right? So the voltage that will resolve to the voltage that will resolve to between 0 and VDD will depend on the strengths of the WP and WN. So as WP by WN tends to infinity, the output voltage will go from 0 to VDD. So this is like a 0 on the y-axis to VDD on the y-axis. The output voltage will go from 0 to VDD. So this is as WP by WN tends to infinity. Now of course, so therefore it is definitely, of course, only once the output voltage goes beyond Vm, the trip point, will we say that it is as long as the output voltage is less than Vm, right? As long as it's only in this region, will we say that it is a functional inverter. That is, you've given the input as logic high, the output has to be less than the trip point of whatever follows it. So therefore, or at least even in fact this is not the case, it has to be within the VIL, the V input low of the next device, whatever follows this inverter. It is only in this zone that we say that it is functional, it is functioning properly, or it is functional. So yeah, so quite clearly it is not true that functionality doesn't depend on the relative sizes. Only if the relative size is such that you get the output voltage to be less than between VIL and 0 or less than VIL, will it be that we say that it is it's a functioning inverter. So this is false, right? So that's question 4. In question 5, we are asked the delay of a CMOS inverter driving another inverter is 50 nanoseconds. If 5 such inverters are connected to form a ring oscillator, what is the frequency of oscillation? So essentially you have inverter 1, inverter 2, inverter 3, inverter 4 and inverter 5, and it's connected like that, and from here to here it is 50 nanoseconds, which means for the signal to come back from starting from there and coming back to the origin, right? It will take how many hops? For each hop it's 50 nanoseconds, so let's count the hops: 1 2 3 4 5. So it's going to be 250 nanoseconds. That is 50 nanoseconds into 5 hops, right? So it's 250 nanoseconds for the for a flip over here to come back down as like that. So therefore that is the so that is the period. So it will be like that, and then there is 250 nanoseconds, and then it will go down like that, and then of course it's another 250 nanoseconds. So it's a period of 500 nanoseconds. So the answer is the answer is 2 megahertz. So yeah. So in question 6 we have that in the figure, if V1 has a period of 5 nanoseconds, so you can imagine that this is a period of 5 nanoseconds, right, with a 50% duty cycle. So you can actually imagine that it's like that, 50% duty cycle, right? with VDD as 1 volt and all capacitance are 4 femtofarad. What is the dynamic power of the circuit in microwatts? So the dynamic power at the V at one node, let's say at V1 node, is going to be C into VDD square into F, right? C is 4 femto, VDD square is 1 square, which is 1, and then F is 1 by 5 nanoseconds, right? So this will be equal to, but of course now there are 5 such nodes, right? 1, 2, 3, 4, 5 nodes, and each node is going to dissipate this dynamic power, and so therefore the P dyne of the circuit is going to be 5 times 4 femto by 5 nano, which is equal to 4 femto into 1 giga, and this is 4 microwatts. So the answer is 4. Yeah, in the previous question the answer is 2, not it's given as 4 over here, but the answer is 2 megahertz. So in question 7, now we have that in the figure, assume all switches and capacitors are ideal and the logic gates have delay and output rise and fall times that are negligible compared to the clock period. So this figure can be analyzed easily by taking the just a moment. This figure can be analyzed easily by realizing that this pair forms a D flip-flop. This is the input, D input. Okay, actually this is the D input and this is the Q output, right? So this it makes it easier to analyze if you realize that that is a D flip-flop with the clock as the input, clock to the flip-flop. This is essentially a master latch and a slave latch, except that it is inverting, that's all. So now yeah, so it's a master slave D flip-flop. So if you have, so redrawing that figure like that, you can get it as the NOR gate, right, whose one output is the, it's a DQ, right, and then DQ, right, and then both of these come here, right? So now let's assume that so this is essentially a state machine and we need to work this out carefully. So we'll call this A and B, right, as the inputs to the NOR gate, which are also the outputs of the flops, are state variables A and B. So we have the current state and the next state, right, A dash, B dash, right? So let's say the current state is 0, 0. Then of course and it's helpful to note that whatever is the current state of B, that will become the next state of A. So B just goes as A, right? And then the next state of that is B dash is just equal to A, and A dash, as you can see, is the NOR of AB, that is A plus B, the whole complement, right? That is plainly obvious, right, because this is A dash, the next state of A, and this is what do you call it, sorry, this is B dash, the next state of B, because it goes to B, and this is A dash, because in the next state it will go to A, and A dash is just the same node as B, right? And of course from here you can see that B dash is equal to A plus B the whole bar, right? So this is that. So if we just work it out, for 0, 0, the next state is going to be 0 1. So for the current state of 0 1, the next state is going to be 1 and then 1, right? 1 and then 0, because yeah, 1 and then 0. And then for the current state 1 0, the next state is going to be 0 0, right? And then for the current state, of course, now we are back to the initial state, right? And you can see that even if for some reason we had some initial state as 1 1, the next state would have become 1 0, right? And then the 1 0 means it will then go to 0 0, and then it will then again cycle through the states, right? So even if it had this as the initial condition, it would eventually come to this cycle, right? It would eventually go to that cycle in the steady state, right? And so the question we have asked, what is the frequency at which N1, right? This is N1, which is just the B input. What is the frequency at which N1 oscillates in the steady state, right? So you can see that N1 oscillates, so the frequency of B will be simply this period, since we are not taking that anymore, it's the steady state. So it will be, so I'm plotting clock, right? So B starts at, so essentially it's a master slave flip-flop with a positive edge trigger, positive edge triggered master slave flip-flop, because when clock becomes high, that's when this switch will close and you'll see something on the output, right? So it's a positive edge triggered flip-flop. And so taking that into account, on the pause edge you will have B, let's say it was 0 before, then it became 1, right? And then on the next pause edge you would have B going down to 0, right? So this is the first one, right? This is 1, and then on the next pause edge, so you would have this as 0, right? And then now on the next pause edge it is still 0, right? That 0 corresponds to this guy, and then on the final pause edge you become 1 again, right? Which will only stay till the next pause edge. So you can see that it has a period of 3 periods of clock, so 3 clock periods for one cycle of B, and so it oscillates at it has a essentially the Tn1 is equal to 3 times T clock, which is equal to 3 into 1 by 3 nanoseconds, which is 1 nanosecond. Thus the frequency is 1 gigahertz, which is, this is Fn1, the frequency, and so the answer is 1. Now if all capacitors, now of course as you can probably guess, all the nodes are going to oscillate at this frequency. This you can work out. You can see clearly that even N2, which is the A of our thing, oscillates at the same thing, and you'll see that the in-between nodes also oscillate. That is, these nodes will not that node is just the output node. So these two are the this and this are the in-between nodes. They will also oscillate at the same frequency. You can work it out. And so therefore the idea is that if all capacitors have a value of 2 femtofarad, now it's just CVDT square F, right? So F is C is 2 femtofarads, VDD is 1.8 volts, so it's 1.8 squared, and F is 1 gigahertz, right? 1 giga. right? So this is 10 power minus 15 times 1.8 square times 10 power 9, which is 10 power minus 6 into 32 point, sorry, not this thing, just a second, 2 femtofarad, right? So it's 2 into 1 femto. So that would just be 1.8 square into 2 square into 2. Yeah, sorry. So this will be, now there are how many nodes? There are 1, 2, 3, 4, 5, right? So that's 5 into this is the power of the circuit. So 5 into that. So that is 5 into 2 into 1.8 square, and that gives you 32.4 into 10 power minus 6 watts, which is 32.4 microwatt. So this is the answer, right? So that is question 8. Now in question 9, at Vn equal to VIL, the gain of the inverter is -1. This is directly from the slides, from the lecture slides. This is the definition of the VIL point, right? So this is the figure that is common for question 10 and 11. We need to find the rise time, fall time for these various signals. T rise is defined as the 10 to 90% time, right? And oh, there's a mistake in this diagram. This should be 0.9 VDD. Oh yeah, so it should be 10% to 90%, and then T fall is of course the 90% to 10% time, and of course in this case TP HL and TP LH are to be found. So if you were to find the T rise and T fall for the various signals, you would find this as the answer. Yeah, so TPHL is the amount of time from input reaching 50 input rising across 50% to the time the output falls below 50%, and TPLH is from the time the input crosses or falls below 50% to the time the output rises above 50%. And if you work that out, you will find that it is option A.